Okay, so in this video we're going to do a process called linear programming, and it's called that because we have a system that's defined by multiple linear equations, or in this case inequalities, linear inequalities, and then we have this objective function g, which in this case our objective is to find the minimum value of g. So before we run right to the calculator, I think it's helpful to maybe get somewhat of a sense of what type of parameters for the viewing window we should consider. And this is also helpful because a lot of times these values end up being corner points anyway. Remember, the goal of this is going to be to get the region of, or the solution region for this system set, and then the corner points are the considerations as far as what's going to optimize, in this case, find the minimum of this objective function g. So I'm going to start by just finding the intercepts. Again, for one, it'll help me figure out what the viewing window needs to be, and like I said, these will be corner points. So if you make x 0, we're going to have just 14/3. Right? If x is 0, we're going to treat this as an equal sign, and then y needs to be 14/3. Divide both sides by 3. If we make y 0, then x needs to be 7. So the same thing for the green. And let's see. If x is 0, y is 8. If y is 0, x is 2. Now we're going to end up getting the slope-intercept form of these lines so that we can put them into the calculator. So if you find it easier to do that first, then we can do that and then come back and find the x, y intercepts. I find it easier to do it in what's called standard form here. X, y, and then for this last equation, if x is 0, y is 4. And if y is 0, x is 8. Okay. Now, we are going to want to put these into slope-intercept form because that's the only form the calculator will accept as far as defining y. So I'll do that. If you notice here, we're going to have, let's see, we got to bring the 2 to the other side. So and we're going to treat it like an equal sign as far as the graph is concerned. So we're going to have a negative 2x. That's a positive 14, but if you see, we had to divide everything by 3. So it's really going to be this gets divided by 3, and that 14 gets divided by 3 as well. So that's the slope-intercept form of the top. And again, we're really doing this in order to get the graph in the calculator, which isn't necessarily always the fastest way to do it. In particular, there's only 2 equations. I like to not even bother with the calculator. But with 3, it becomes more difficult to figure out where the intersection points are. So I like to do this in the calculator when it comes to 3 systems like this, or 3 equations in the system. All right, so the green equation, let's see, we're going to have to give me the green pen back. Thank you. And let's see, just bring that 4x over. So it's going to be equals negative 4x plus 8, not divided by anything there. Oh, I turned that one green. I see. Well, that's not good. This was the red. Let's see, properties, red. There we go. And that was the green one. Okay. So that leaves the blue one here. And get a blue pen. So see, for the blue one, we would have to bring the x over. So we get y equals, that's going to be a negative x. And then we're going to divide everything by that 2. So we'll say it's negative 1/2 x. And then that will be a plus 8. But we're going by 2, so it's a 4 plus 4. Okay, so let's go to the calculator now, because I think a lot of this is going to be suitable for the calculator at this point. So in the calculator, notice this is why we took the time to write slope-intercept form so we could put them in. We've got negative 2. Oops, let's see, that's not even on now. There we go. Negative 2 divided by 3x, or negative 2/3 x, plus 14/3. Our other equation, negative 4x plus 8. You know what? I'm tempted to stick with the same color, so let me actually, I don't know if you noticed this, but just for the instructional purposes, it doesn't matter if you do this yourself. I'm going to put the red function where this color calculator graphs in red. So that would be, in this case, y sub 2. Negative 2. I'm just doing this just to keep it color-coded. Like I said, it doesn't matter what order you put them in. So we got negative. You can put this in lots of different ways. This negative 2. I think it's just negative 2 divided by 3 times x. It's perfect. If you're not sure, you can always use parentheses. You don't need them there. So it's plus 14 divided by 3. And then I said the green function, so I'm going to go down to the green graph, which is y5. That's negative 4x plus 8. And then the last one is blue, so I'll go back up to y1. And that was negative 0.5 or a half x plus 4. So we got all the graphs in there. I put them in that order just to get the colors to match what I have here. Well, let's set the window real quick. Now this y-intercepts give us a good idea what the window should be. So we notice so we're not really going outside of the value 8, right? 14 thirds is something a little less than 5. So you know, the biggest y value I'm seeing is 8. The biggest x value is 8. So a standard viewing window would be fine. Now the other thing to consider is that x and y are positive values, right? That's another thing that was included in this set. So that means we only care about the first quadrant, right? That if here's the xy plane, we only care about, this quadrant here. This is the only spot where both x and y are positive. So we're only interested in that portion anyway. Let's restrict the window a little bit. Let's see. Our x min, well, we said it has to be bigger than or equal to 0. I like to see a little bit to the left, though, so maybe I'll make it like negative 1. My x max, well, we said the biggest x was an 8, so maybe I'll just make it a 10. The y min, again, y is no smaller than 0. I like to see a little bit below the axis as far as the window is concerned, so negative 1. We could make really anything you want, but it's a preference here, negative 1. Biggest y was 8, so I'll just make that 10 again, see a little bit above the 8. And now if you graph it, the calculator will plot out a good picture of what we need to work with from here. Okay, now you actually can have the calculator do the shading for you as well. I do not think it's worth it. So a lot of things didn't go wrong. Maybe if you have a newer calculator and it's color-coded, that might not be that hard to do. In particular, though, what goes wrong is people, when you solve for y here to get everything in terms of y equals mx plus b, because they're inequalities, you have to remember if you ever divide by a negative coefficient, that's going to flip the inequality symbol around. And a lot of people mess that part up. That being said, I could show you how to get this graph in the calculator real quick since it's I got 15 minutes, so I got about 7 minutes left. That should be good time. So if you consider this, if I leave the inequality symbol in there, I never actually divided by a negative, so it's going to stay as greater than or equal to. Same thing's true for the green line. That would be greater than or equal to, and then same with blue. I never divided by a negative, so that's going to maintain its greater than or equal to. So you actually can put it in the calculator that way. If we go back to y equals, if you highlight this bar here, and you hit enter, you should be able to go down to style. If you have an older calculator, this is a little bit, it's essentially the same, but the menus are a little bit different. Let's see, now I don't even see, oh, here it is. The style is actually fine. This is the older calculators, you have to go off these lines, but this is actually meant to be more user-friendly. Let me show you this. Just where the y equals, there's the greater than or equal to. And then the style is actually, this is the greater than or equal to. If you have an older calculator, it's going to keep hitting enter on that little line where it says y equals this piece here until you get this symbol here. This is the old symbol for greater than or equal to, but this newer calculator, this operating system tells you this to make it a little more user-friendly. Okay, so we're going to do that for all of them because they're all greater than or equal to. So we'll hit OK here, and then we'll go down and do the same thing. Hit enter. Need another greater than, oops, or equal to right there, hit enter. And then this was also a greater than or equal to. Okay. And I'll show you how to do it without the calculator too, because sometimes I think even though the calculator is nice, it isn't always the most efficient approach. Okay. Now, with the color-coded calculator, especially if you're able to blow it up big like this, you might be able to tell what region we're interested in. Now, we're concerned about the region where everything overlaps, right? We want to know, if we're going to satisfy the system, we have to satisfy everything. So it looks like we got to be to the right of the green. We've also got to be above the blue, or to the right of the blue, however you want to see it, and then to the right / above the red. So the region that's being suggested here, I think it might actually be helpful to get a little hand picture anyway. That's why I have this here, right, to show you how I would do this without the calculator, or how we can make sense of this. Because that's kind of the thing. The calculator can almost look a little jumbled in a sense, because this when it starts to overlay like this. But let me show you. I mean, at least tells us what the region is, right? It looks like it's going to be to the right of the green, above the red, and above the blue. So all that there. But just briefly, remember you can always do a test point, right? Like relative to the green, if I plug in 0, 0, I get 0 is greater than or equal to 8. Well, since 0 is not greater than or equal to 8, I don't want to shade towards the point 0, 0, which is on this side. I want to shade away from it. So that would tell me pretty quickly, without having to go into the calculator, it's as far as the shading is concerned. We're to the right of the green. Same's true with the blue. If I plug in 0, 0 into the blue equation, I get 0 plus 2 zeros is still 0. So 0, since it's not greater than or equal to 8, and here's the point 0, 0, I want to shade on the other side, which is, again, to the right or above the blue. And then if we do the same thing for the red equation, you plug in 0, you plug in 0, you get 0 is greater than or equal to 14. Again, that's a false statement. So again, if it was true, we would shade towards it. But since it's false, we want to go away from this point 0, 0. So we want to go on this side of the red, right? So that's a real quick way to see, okay, well, then it must be this region here. This is the region that is to the right of the green, or above the green, above the red, and above the blue, right? It's this little piece here. It's hard for me to trace out almost because that blue and red are so close to each other right there. But everything to the right of that black line I laid out. That's the solution region. So we consider that. Next thing is to get the corner points, because those are going to be the options for the objective function as far as a minimum value. So we've got one corner point here. We've got one right there. We've got one right there. And we've got one right there. Right, that's where the blue line crosses. And I realize I'm getting low on time, so I got to pick it up a little, I guess. But luckily, we've done some of the work already. Look, this is just the y-intercept for the green line, right? So that corner point right there is 0, and then we've already found it, right? In green, the y-intercept was 8. So that's 0, 8. This is the x-intercept of the blue line, right? It's crossing the x-axis. That is where y is 0. We've already found the x-intercept in blue. It was 8, 0. So this corner down here is 8, 0. 8, 0. So we got 0, 8, 8, 0. I'm tempted to change the color of this. I'm trying to go for some sort of a color code system here. All right, 0, 8, 8, 0. The other two are the intersections of whether it's the green and the red or the red and the blue. And in either case, we have to solve the system for that. So I'm actually going to not do that part here algebraically because I assume that you can do that. And I'm trying to save time on this video. But remember, the red and blue, we got to solve this system here. You can do that as a matrix in the calculator, or you can do it just by doing an elimination method. We're going to solve that system. And then also the red and blue point is the intersection. So you have to solve the system with this equation and this equation. Right? And you can do that again, as a matrix operation in the calculator, or you can take the time to do the elimination method. So I'm going to pick up there. Give me 1 second, Paul. So this here, 2, 4, is the ordered pair right here that's associated with the intersection of the green and the red line. And then this point 4, 2 is the ordered pair associated with the intersection point here, the red and the blue. Now, the other thing you could do with that is outside of solving the system is you could read the graph if you feel confident. But in most cases, I wouldn't advise that because imagine these are fractions or something, you're not going to be able to do it. But in theory, if they're integers like that, you can read the graph. Now, the only thing that's left to do is to plug all 4 of these points, the xy pairs, in for, if you notice there's an x and a y, plug them all in and then accept the smallest value of that g as the minimum. So again, I'm going to pause to do that because I have a 15-minute time limit. So again, here's G, and I evaluated G at all 4 of those corners, and it turns out the one that gives the minimum, this is a bit of a strange problem because it turns out the minimum is 240, so the minimum is 240, but it occurs at 2 different places. It occurs at 0, 8, and it also occurs at the 2, 4. So we have a single minimum. The minimum is simply 240, but again, it occurs at 2 separate ordered pairs. Hope that helps, and let me know if you have any questions. Thank you. Bye. Right on the dot, 15 minutes.